Hello guys, this is Prime Concept. In this video, I want to consider the concept of modulus, or what you know as magnitude of a complex number. If you're meeting me for the first time, you're welcome to my channel. If you're a returning subscriber, you're also welcome to this channel. So join me as we expand on the concept of modulus, which is also known as magnitude of a complex number. Now, what is the magnitude of a complex number? First, we want to recall that our complex number we usually denote as z equals x plus iy. So that this, where x, remember that x is the real part and then y is the imaginary part. Now say we want to locate this on a plane which we know as Argand diagram. We're going to represent our y like this. So this is our y, and then our x this way. This is our x. Therefore, the resultant, or the modulus, or the magnitude of x and y is going to be a line through their point of intersection. So this, which is the modulus, is denoted by this symbol. So we're going to see how to find this modulus. So if I complete this diagram, you would also see that if this is y, this distance should also be y, such that this angle becomes theta, which is what we know as argument we're still going to mention after the modulus. Now, the modulus of a complex number is obtained by using the Pythagoras theorem from this diagram on the board. So modulus is denoted by the symbol. The symbol for modulus is this. Whenever you see two straight lines enclosing a complex number, simply means find the modulus or find the magnitude. Now from this diagram, seeing that this is a right triangle, we can apply Pythagoras theorem to solve for this hypotenuse. So which is going to give us z would be square root of x squared plus y squared. So this is simply Pythagoras theorem. And this formula here on the board is the formula we can use to find the modulus of a complex number. Now, one of the things I want you to note from this formula is that modulus would always be a positive quantity. That is one point I want you to note. Number one, it is always positive. So the modulus of a complex number would never be negative. And number 2 point I want you to note is that when you're finding modulus, you don't include I. I is not included. The only thing you use is the coefficient of I, which is y. So I is not included. I is not included in the formula. So it's very important for you to note this. So this is how you can find modulus of a complex number. And the other thing that follows is the argument. Argument represents angle. So whenever you hear argument in complex number, simply means find the angle. So we're later going to learn that we have a special kind of argument which we call principal argument. For now, what we're trying to do is ordinary argument. So the ordinary argument is just this angle theta, which is actually this. So this theta is going to be the tan inverse. But let's go this way first. So say I want to find tan. Of course, tan is opposite over adjacent. So tan theta is going to be opposite. I'll use this over adjacent. Why am I using this? Because I'm dealing with the first quadrant. So it means that these two quantities are positive. So we'll be using this to find argument, so that at the end we can determine which quadrant the complex number falls. That is why we'll be using the absolute value. So it means when we want to find this, we'll always take the absolute value of y and x. We want them to always be positive. So at the end, we'll determine which quadrant it falls and get the actual angle. So our argument theta is the tan inverse of y over x. This is our argument, and this is the formula for modulus of the complex number. So we're going to take one example, after which we're then going to look at the properties of modulus. Properties of modulus. So very quickly, say we have z equals 1 plus I, find the modulus and argument. Remember, argument means what? Angle. So these are the two things we want to find. Now, first, we want to identify our x. In this case, our x means the real part of the complex number. So meaning that x in this case is what? Is 1. And our y is the imaginary part, which is the coefficient of I. And the coefficient of I is 1. Once there is no number, it means it is 1. So y is 1. So since you have your x, you have your y, then we want to find the modulus, or what you call magnitude, which is equal to x squared plus y squared. So this is equal to square root of x is 1 all squared plus y is 1 all squared. So this would give me the square root. 1 squared is 1 plus 1 squared, which is 1. So I then have the square root of what? 2. So it means my modulus is root 2. So I've been able to find that. The next thing I want to get is the argument. So the argument we've established is tan inverse of y divided by x. So I have tan inverse of my y, which is already positive, is 1. My x positive is 1. So I have tan inverse of 1 divided by 1, which is 1. So I have tan inverse of 1 is actually 45 degree. But most of the times in complex number, we like or we prefer to use the angles in radian. So to convert this to radian, I would simply multiply it. So I would say 45 times pi over 180. So when you reduce this, you'd finally get pi over 4 radian. So it's either our answer is 45 degree or our answer is pi over 4 radian. Alright, so I believe this is very clear. Now very quickly, to the end of the video, let's quickly talk about properties of modulus, or properties of magnitude of a complex number. Properties of modulus. So one property that is important for us to know is that the modulus of a complex number, if the modulus of a complex number is equal to 0, this would only be true if the complex number itself is 0. So the modulus of a complex number can never be 0 except that the complex number itself is 0. That is when the modulus becomes 0. So this first thing you should know. Number 2 property I want you to also know is the inequality property, which you can always test. When I give you these things, you can test them with values and confirm that they are true. One is, I want you to know that the real part of every complex number would always be less than or equal to the absolute value, or the modulus of the real part. And then the modulus of that real part would always be less than or equal to the magnitude or modulus of the complex number itself. So what this thing is trying to say is that if you have a complex number, the real part of a complex number at every point in time can never be greater than the modulus of that complex number. So anytime you find, just like what we did, the question we solved, we solved the question where we said z is 1 plus I. And you notice that the real part of z is 1. But then the modulus of the complex number is root 2. Root 2 is actually 1.414, which is greater than 1. So what this is telling you is that the modulus would always be bigger than the real part of the complex number. The modulus would always be bigger than the modulus or magnitude of the real part. That is what it means. At most, they will be equal, but this can never be bigger than this. That is what this is trying to say. Now, same thing is applicable to the imaginary part. You can still say this same thing, that the imaginary part of a complex number would always be less than or equal to the modulus of the imaginary part, which would always be less than the modulus of the complex number itself. Same scenario. Then another thing I want you to note, number 4, is that the modulus of conjugate of a complex number. Now, if you take the conjugate of a complex number and you find the modulus, it would always give the same result as the complex number, the modulus of that complex number itself. Now, this should be very clear. What I want you to do is to pick some complex numbers by yourself and try to evaluate and verify that this property is true. Now, the modulus of conjugate would be the same as the modulus of the main complex number. So that is true. And say we have z equals 1 plus I. Let us see the conjugate of this. The conjugate of this is going to be 1 minus I. Now let's find the modulus of the conjugate. The modulus of the conjugate is going to be the square root of 1 squared plus the coefficient of I is minus 1. So I'll say minus 1 squared. So that this is going to give me 1 squared is 1 plus, then minus 1 squared is still 1. So I'll have root 2. And you notice we've already found the modulus of z itself in our previous question, which is still root 2. So the modulus of z and the modulus of z conjugate are root 2, which is the same. That's what this property is actually telling us. So property 4. Then property 5. Property 5 is if you multiply a complex number by its conjugate, the result will be the modulus, the square of the modulus. So this is true. We've seen this when we learned properties of conjugate. We saw this. We saw that z times z conjugate is actually x squared plus y squared. In the same way, you should know that since modulus is actually square root of x squared plus y squared, it means that if I bring this square root to this side, by how do I bring this square root to this side? I can decide to square both sides. So that this can fizzle this, and then I'll have modulus squared equals what now? X squared plus y squared. So you would see that this is this and this is also this, and that is why we are saying that this is actually equal to this, right? Yes, so take note of that. Number 6 property I want you to note for modulus is that if you have multiplication, say you have z1 times z2 and then you take their modulus, this will give you the same result as taking the modulus of z1 before multiplying with the modulus of what? Z2. This will give you same result. This same thing is applicable to division. Number 7, say you have z1 divided by z2 and you're taking their modulus. What this thing means is that you first of all divide them before you take the modulus to give you the same result as taking the modulus of z1, taking the modulus of z2 before you do what? Before you divide. And then I want to add one more, which is a bonus property. We call that triangular inequality. And I'll be proving this in my next video. For now, I'll just add it. Number 8 is what we know as triangular inequality. So say we have z1 plus z2. You add two complex numbers, then take their modulus. This would always be less than or equal to the modulus of z1 first before you add it to the modulus of what? Z2. So this is what you know as triangular inequalities. Watch out for my video where I'll be doing a proof for this particular property of modulus. So at this point, we are done with the properties. There are still more, but then these basic ones you should know. So at this point, we are done with the properties. In my next video, I'll be diving into principal arguments. I will let you know the two types of arguments we have. In this video, we just considered the ordinary argument. In my next video, I'll look into principal argument of complex number. We'll then look at De Moivre's theorem, very important, and the applications of De Moivre's theorem. So do well to stick in this channel. Watch out for my next video. Thanks for watching Prime Concept.